Welcome to the next video on predicates. Now this video is one of the most exciting video, if not the most exciting video of this entire chapter, because we are going to take a little trip down memory lane and pick up some nice shiny things while we're down there. It's going to be great. October is excited, even though I'm recording this in November, but she's excited anyway because she's excited to learn about how do predicates have to do with relations. So remember what a relation was. A relation was a set of ordered pairs, right? If we had, if we said that A is related to B, that means that the ordered pair, A comma B, was in that relation, right? Relation was a set of all of these ordered pairs. So A being related to B should sound familiar. And again, relations don't have to be ordered pairs. They could be ordered triples, or any kind of tuple, right? It could be an A, comma, B, comma, C, an A, comma, B, comma, C, comma, D. It could be as many as at once. It just has to be the Cartesian product, remember, of the domain and the codomain. But the domain could actually be a Cartesian product itself. So anyway, I won't dive down into that too much, but yeah, relations are sets of ordered pairs. So remember in the last video, right, we introduced a predicate with two inputs, right? This predicate was the in city of predicate. For example, SPSEC is in the city of Olympia. That's a true statement, has a truth value of 1, okay? Jason is in the city of Pismo at the moment is false, okay? So from any predicate, okay, and especially easy to see with predicates of two inputs. With any predicate, you can very naturally define a relation, right? Where A is related to B if the truth value is 1. So that's really, really exciting. Let me write this a different way, okay? So let's say that we have in city of can be thought of as a relation, right? Two things are related if the first thing is in the city of the second relation. Is this reflexive, right? We talked about all these things that relations could be. Is this reflexive? No, I don't think so. I don't think Olympia is in the city of Olympia. I don't think that really makes sense. Is it symmetric? If I'm in the city of Olympia, is Olympia in the city of me? Ooh, I do like the sound of that, but no, it's not symmetric. And is it transitive? No, not really. So, right, this is a relation, but because the domain and the codomain of our relation are kind of different things, it's of course not going to be an equivalence relation, but just trying to jog your memory of some of those concepts that we talked about earlier this quarter. Okay, so this isn't a relation. And let's look at this following statement. I'm going to make a statement here. A is related to B that has a truth value of 0 or 1 if and only if, or again, this is our equiv logical operator, in city of A comma B. This is a tautology. This is always true. If we made a truth table for all the different values of A and B, we would see that yes, this is always either true or false when this matches that truthness and falseness. That's not really great English, but you know what I'm saying, right? So this is always true. This is an identity. This is a tautology. We're really seeing so many things like come into play. So many things that we've talked about in this quarter, right, are all like interlacing, which is one of the exciting things about getting to these further chapters in a class. We talk about a lot of stuff and we use those stuffs as building blocks to build other bigger and cooler things. And here's why this is so exciting. And this is one of the most exciting things in all of math. This is the reason why math is exciting, because all of that boring stuff that you learned about relations, and you learned a lot of boring stuff about relations, or at least you were exposed to a lot of boring stuff about relations. There's so many boring things in theoretical math, and I'm a mathematician, so I think a lot of it is cool, but there's so many boring things in theoretical math that apply to not boring things. So all these things that people love to study about relations, maybe you don't care about relations, but some people love to study about relations. Since relations are essentially identical to predicates of this type, all of that stuff that people are studying about relations applies, and we can use that powerful machinery from all that research and study to these predicates. So all of this stuff is going to apply to our predicate logic. All of this stuff applies to the applications of predicate logic. So all those math nerds studying relations have their stuff being used by people using predicate logic in machine learning and like AI and stuff. So it's very exciting, very powerful. And that's one of the cool things about math, right? Mathematicians study a bunch of like theoretical stuff, and that theoretical stuff, whenever we connect these things, whenever we connect theoretical to the practical, then we get to use all of that powerful machinery and results, which is pretty darn exciting. So we could, now talk about injectivity and the properties of injectivity. We could talk about surjectivity, bijectivity, the idea of an inverse. We could talk about equivalence relations. All this stuff that works for relations, we can also apply to predicate logic and predicates. We're not going to do that here, but I just wanted to make that connection and get you to kind of realize why that connection is important. Why did we introduce relations? It's so we can use that mathematical power from all that theoretical work that people do. Okay, I'm going to get off my soapbox. It is very exciting. We're going to introduce quantifiers. So there's two kinds of quantifiers that we're going to talk about. I think most of you, if not all of you, have seen these before, but here we are going to do. So specifically, remember that the idea of propositional logic was we had these just isolated propositions. It was simple, but we couldn't really do much to them. But predicate logic, on the other hand, predicate logic has a lot of modularity. We can make one thing do a lot of different things. And quantifiers really, really help with that. So we have the universal quantifier, which I also have introduced in chapter 3 under a different name. The for all quantifier, written like an upside down capital A. Okay, so that means for all x. And then we also had the existential quantifier. And no, it's not talking about existentialism. It's talking about whether something exists. It's that kind of existential. Does something exist? Not what is the meaning of existence. We'll save that for another class. And that looks like a backwards capital E. Kind of funny, this is an upside down capital letter. This is a backwards capital letter. But here we are. And what that means is there is an X, or there exists an X. And now we're going to play with that a little bit with a lot of examples. Okay, so some examples for this are, for all, again, we're tying into our intro to predicate logic video. For all X in US, and let's say here that US is the set of all US states. So for every US state is what this means. For all things that are US states, we can say, I'm actually not going to write a comma there, has gov of X. Remember, we introduced this predicate in the last video. This predicate says, well, this is going to have a truth value of 1 if X is a state that has a governor, and it will have a truth value of 0 otherwise. So we're saying that for every US state, this statement. So this is always true. Every US state has a governor. Okay? Likewise, we can introduce our existential quantifier with another similar example. There exists an X such that has gov is not true. Well, that's also true. Now notice one very, very important difference here. On the left, I specified what X was. I said we're looking at all the X's, but we're only looking at all the X's in the set of US states. Now here, I'm not telling you what X is. I'm saying X could be anything. It doesn't have to be a US state. X could be Guatemala. X could be oatmeal. X could be the pancakes I ate this morning. X could be my cat. Does my cat have a governor? I sincerely doubt it. There's certainly there's kind of an anarchic. It's anarchy in my cat's head, I'll tell you that much. Okay? So this is also a true statement. There are many things that don't have governors. So this part of the statement is very, very important when you're using quantifiers. Be very clear to specify what kind of x's are you even talking about here. So let's do some examples. And like I often like to do, I want you to look at these examples, pause the video, and determine whether they're true or false on your own, and then we can talk about them together. All right. So let's look at a few different ones. The first one will be for all x has gov of x. This is a statement. It will either be true or it will be false. The next one, for all h in H, and let's say H is going to be the set of humans. Adult of H, XOR child of H. And let's do one more. For all H just in any set, human of H implies adult of H. That's not how you spell adult, silly. XOR child of H. So what do you think for these? Pause the video if you haven't already. Look at these. And again, I cannot stress this enough. It's really, really important to specify where your x is coming from. If you don't specify where your x is coming from, all right, that's too many circles. If you don't specify where your x is coming from, really silly things can happen. So this is going to be false. It's true for all states, US states, but it's not true for just anything, right? We already talked about it. My cat doesn't have a governor. My oatmeal doesn't have a governor. My pancakes don't have governors. My lamp doesn't have a governor. All right? We would need to specify what kind of x's we're looking at. B, we do specify. For all h coming from the set of humans, so all humans, are all humans either an adult or a child and not both? Okay? And here, again, we really get into some nitpickiness. It depends on how you define these functions, right? It depends on how you see the world. Now, if you define adult, if you're saying, let's say that somebody is 18 or older, and you define child as younger than 18, then yes, this is true. Every human who's alive is either an adult or a child, but not both. Now, again, if you define these differently, then there are many people, there are many adults who are also children in my experience, and there are some children who unfortunately are kind of adult-like. Anyway, I'm not gonna, some people have more responsibility than they ideally should. Anyway, that's a conversation for another time. But again, it depends on how you define these functions, but if you define it this way, sure, this can be true. All right. Letter C. For all H, period. There's no specification this time in letter C. For all H, period, if H is a human, then either, oops, I forgot my H here, then either H is a child or, XOR, H is an adult. Is this true? And we have to be a little careful on this. Remember that implications are kind of funny things. So the only way an implication can be false is if, right, the only way this can be false is if we have a true premise and a false conclusion. That's the only way that an implication can be false. So can this happen? Is it possible for H to be a human and not be either an adult or a child? Well, we just showed in part B that if H is a human, then it is either an adult or a child. Okay? So we'll never be able to make this implication false. And pick any h that you want, and you'll see that this is true. I actually don't need to erase that, right? So any h you want. You think we could pick oatmeal. Okay. If oatmeal is a human, then oatmeal is either an adult or a child. But oatmeal is not human. So the statement doesn't apply. So this does have a true value for h being oatmeal. And anything that's not a human, actually, you're just going to find out that this if-then statement doesn't even really apply. So it's going to be true by default, right? This doesn't really come into play. We don't get this far. We don't even enter the if-then statement for things that aren't humans. And if they are humans, then yes, we have this being true. So by that logic, this will be true as well. All right, so there's some other things that we can do with this. I'll run through that pretty quickly because this video is going long. I knew it was going to be long because there's so many fun stuff to talk about with relations and quantifiers. It's a good time, right? So there exists an x such that has gov of x. What do you think about that one? There exists an x such that president of x and black of x. All right. What about there does not exist a president such that president of x and female of x. I'm going to use the word woman. All right. What do you think about these statements? The last one. One more. It is not true that for all x has gov of x. Pause the video. Think about these, and we'll discuss. So there exists an x, any kind of x, right? We're not specifying what kind of x. There's some kind of x somewhere such that x is a state that has a governor. Well, that's true. In fact, we said, oops, that's not how you write true. We know that's true because we said it was actually true for all of certain x's, which means it's certainly true for a lot of x's. It's not true for every x, but there's certainly at least one, right? Does there exist an x such that x is or was a president? I guess it depends on whether we're talking about current or past. But yes, right? There does exist one president at the current time who that is true for. Oh man, this is really, I'm recording this on November 8, 2024. So some of these are, yeah, anyway. There does not exist a president, again, at the time of recording this video, such that that person, is a president and is a woman. And so this one is also true. That is not the case. And how do we read this last one? This last one is saying not for all x has gov x. So we can, again, break this down. We could use a truth table if you wanted to. Let's just break this down first, and let's look at this statement. Is it true for all x has gov x? And we said no, right? Oatmeal does not have a governor. So this part is false. And then we just combine it, right, with this unary operator. Unary because it's only applying to one proposition instead of things like XOR, which applies to two propositions. That would be a binary operator. So this one is now true. So these are all true. Okay. It was an exciting video for me. Hope you survived. We got another one. The next two will be pretty short. We'll talk about how do we interchange quantifiers. We'll talk about the value of precision, and we will wrap up this entire chapter before we move on to proofs, which will be fun. Have a good one. Let me know if you have questions.